What if I told you that force fields already exist, and at the same time take you through the real science of sci-fi energy shields? Today we're going to break down force fields and energy shields. What parts are real, what parts are sci-fi? And then the one brutal law of nature that ruins almost every shield idea ever imagined. When sci-fi talks about shields, it usually means one of three things. Some sort of personal shield, a glowing bubble around a person that blocks bullets, blades, lasers, that sort of thing. Or a vehicle or starship shield, some sort of energy barrier that absorbs incoming fire and recharges between hits. Or, lastly, some sort of planetary shield, a massive defensive dome protecting the entire world. These all look similar, shimmering, glowing barriers, but scientifically they're wildly different problems. So, let's start with the most fundamental issue. Anything that blocks matter must also block energy. And that's where things really start to fall apart. If your shield stops incoming bullets, shrapnel, explosions, then it must also stop air, heat, light, sound, and radiation, which unfortunately means a perfect shield would suffocate you, cook you, blind you, and deafen you. Sci-fi usually hand waves this away by saying something along the lines of it lets friendly things through. Unfortunately, physics doesn't accept friend requests. Let's start with pure energy shields. This is where most sci-fi goes wrong. People imagine shields made of pure energy. But energy isn't a material, it doesn't have structure, it doesn't form walls. To block physical objects, a shield must be made of matter, or a field that interacts with matter. And that only really leaves us with two real options. Option 1, an electromagnetic field. This is great for charged particles and stopping those. However, it would be useless against neutral atoms, bullets, rocks, people. A bullet doesn't care about your magnetic field. Option 2 would be a plasma shield. This is a little more promising. Plasma can be shaped by magnetic fields. Plasma is extremely hot. Plasma would react violently with incoming objects, stopping a lot of them. But plasma has a lot of problems as well. It radiates insane amounts of heat. It requires an enormous amount of continuous power, and it would essentially flash cook anything inside it. And it's also wildly unstable outside of lab conditions. Plasma shields are less force fields and more portable stars that will kill you. Okay, so here's where the real science gets interesting. We already use a real force field-like technology. Not the sci-fi version, but actual real force fields. Here are 3 examples. Example 1, magnetic confinement. We use these force fields in fusion reactors to hold super hot plasma and prevent it from touching the physical inner walls of the reactor. That's a real force field. Unfortunately, it only works on plasma, not bullets. Example 2 is plasma windows. This is a real force field that NASA and various laboratories use to separate vacuum from air. These allow particles or radiation to pass selectively through. Again, a real force field-like behaviour. However, these are very fragile, very power-hungry, and extremely specialised. Real example 3 is a laser-induced plasma mirror. These high-energy lasers can create temporary plasma barriers that reflect radiation, just like a real force field. This is probably the closest thing we have to a real sci-fi shield. Unfortunately, it only works for microseconds in a controlled environment and at an enormous energy cost. So what about the way sci-fi shields always eventually fail? There's a reason shields always fail dramatically in sci-fi stories, percentage dropping with each hit until the Enterprise pulls a rabbit out of the hat and escapes, that sort of thing. Real shields, however, would fail in one of 2 ways. The first would be thermal overload. Blocking energy means absorbing it. absorbing enough incoming fire, and your shield doesn't drop dramatically like in the sci-fi film. It turns into a bomb. The other way a real shield would fail would be power scaling. Stopping a handgun round, a bullet, is one thing. Stopping an artillery shell is another. Stopping a meteor, an entirely different requirement. These power requirements don't rise linearly with size, mass, force, but rise exponentially. A planetary shield would need power comparable to a small star, with cities size cooling systems, an infrastructure that becomes the planetary system's biggest target for incoming fire. Some sci-fis have shields that only activate when hit. That helps a little bit, but it introduces new problems as well. There's a reaction time limit, a sensor lag, there are false positives, friendly fire misclassifications, and at high speeds a projectile hits before the shield even knows it exists. At relativistic speeds, nothing reacts in time. So let's do a compare and contrast on how some shields actually work across popular sci-fi. First up, let's look at those personal shields in Dune. Dune actually has one of the most internally consistent shield systems in sci-fi. These shields block fast-moving objects, but allow slow-moving objects through. They turn ranged combat into knife fights. From a physics standpoint, that's actually quite clever. It sidesteps the air problem, it avoids a total thermal lockdown, and it acknowledges the energy limits. But here's the cheat. A shield that detects velocity with perfect discrimination and reacts instantly at molecular scales would require an absurd sensing precision and energy control. Dune doesn't break the physics outright. It does assume a sensing technology that's almost impossibly good. Second up, let's look at those Star Wars starship shields. Star Wars shields behave more like rechargeable hit point bars, energy buffers that absorb damage. They stop lasers. They sometimes stop physical objects. They magically fail at dramatic moments. The issue? They kind of ignore energy conservation. If a ship absorbs gigawatts of laser fire, explosions, kinetic impacts, that energy has to go somewhere. In reality, a Star Wars shield wouldn't flicker. It would catastrophically dump heat and radiation, turning the protected area into a furnace. That would be great cinema, but terrible thermodynamics. Third, Star Trek deflector shields. Star Trek is fascinating because it almost explains those shields. They're often described as deflector shields, navigational shields, layered field systems. These concepts loosely resemble electromagnetic particle deflection, radiation shielding, micrometeoroid protection. The problem is they routinely stop torpedoes, asteroids, massive kinetic impacts. Electromagnetic shields don't stop neutral matter. A rock doesn't care about your deflector dish. So Star Trek shields work narratively, but only by quietly ignoring the basic particle physics. Next up, let's look at The Expanse. There's no shields at all. The Expanse does something radical. It removes shields entirely. Instead, defense comes from distance, speed, armor, point defense cannons, and really not getting hit in the first place. This is by far the most realistic approach. There's no magical barrier, just brutal Newtonian physics. Less flashy, but far closer to how real space combat would actually work. Lastly, Halo. That has rechargeable energy shields. Halo popularised the modern video game shield of absorbing damage, recharging after a pause, failing predictably. This model assumes near-perfect energy storage, instant heat dissipation, and no real structural fatigue. In reality, repeated energy absorption causes material degradation, thermal stress, and in the end, catastrophic failure, not recharge. Halo shields behave more like narrative stamina bars than physical systems. So across nearly all sci-fi, shields rely on at least one impossible assumption. Whether this assumption is perfect discrimination between threats, infinite cooling, free energy storage, or instant reaction time, or even selective physics, as in this passes, that doesn't. Every franchise picks its poison. So if I were to rank the sci-fi shields by realism, I'd probably have to go for the expense in the most realistic top spot by refusing shields altogether. Second, I'd probably place Dune. It's quite internally consistent, but technologically extreme. Third is those sort of Star Wars, Star Trek, Starship shields. They're conceptually rich, but physically fragile. And last is those Halo-style shields. Very cinematic, but not really physical, not really in line with real science. The closer a story gets to real physics, the fewer the glowing domes it allows. In reality, the most realistic shields aren't glowing domes, but are a much more boring layering of various systems. Active interception, point defense lasers, ablative armor, redundancy, distance. In other words, relying on not blocking the hit, but stopping it from ever reaching you, which is dramatically less cinematic, but more brutally realistic. So, could we get sci-fi shields to really work? Short answer, some shield-like effects already exist. We already have them. But true all-purpose energy shields, almost certainly not. Not because we're bad engineers or scientists, but because the universe has rules and force fields break a lot of them. Sci-fi shields aren't impossible because of technology. They're impossible because they demand physics that doesn't exist. I'm Dr. Dan Stokes, and if you enjoyed this breakdown, subscribe for more science versus sci-fi reality. Maybe tell me in the comments, which sci-fi shield do you think is the most realistic or the most ridiculous? See you next week.